So here's a problem from chapter 12 that just says a large room contains moist air at 30 degrees C and 102 kilopascals. So essentially atmospheric pressure. The partial pressure of water vapor is 1.5 kilopascals, and we need to determine the following: relative humidity, the humidity ratio, which your book uses the words humidity ratio, and by that they mean the absolute or specific humidity. C, the dew point temperature in degrees C, the mass of dry air in kilograms, if the mass of water vapor present in the air is 10 kilograms, and we need to determine the volume of the room itself. So I'm going to work through this two different ways. The first way is just simply using the equations to solve for these things, and the book as necessary. The second way I'll work through it is using the psychrometric chart, because we have a psychrometric chart for standard atmospheric pressure, 102, 101 kilopascals, and we can use either method, equations and tables, or the psychrometric chart. So using equations, if I want to know the relative humidity, that's going to be for part A, the relative humidity is this value phi, which is the ratio of your vapor pressure with respect to the saturation pressure at the temperature present in your room, in this case, or in your environment. So in this case, the temperature that we're considering is a 30 degree C temperature environment. P sub G, or your saturation pressure, is just simply from table A2. We go to that table, we look up 30 degrees C, and we can look up P sub G at 30 degrees C. When we do that, we find out that P sub G at 30 degrees C is equal to 4.246 kilopascals. Now that's written in bars in the table, but we can convert it to kilopascals. 4.246. So the relative humidity phi is just simply the ratio of our vapor pressure, which is provided, 1.5 kilopascals, to our saturation pressure at 30 degrees C, 4.246 kilopascals. This value in the denominator here represents, well, the vapor pressure, but we recognize that the relative humidity phi is a measure of how much air is present within, or how much water is present within your air with respect to how much water can your air hold. And the amount of water that air can hold is a function of temperature, because, well, in this case, we recognize that the saturation pressure increases as temperature increases. Therefore, the amount of water that the air can hold also increases with temperature. This turns out to be 0.35 or 35%. Either way you write it is fine with me. That's the answer to part 1, or part A. Part B is the humidity ratio. The humidity ratio, well, we have an equation that relates relative and absolute humidity to one another, or we can just say that the humidity ratio, the absolute humidity, is 0.622 times PV over P minus PV, where this P here is your total pressure, your atmospheric pressure. Plugging in 0.622 times our vapor pressure, that's provided, 1.5 kilopascals, divided by our total pressure, again, that's provided, that's 102 kilopascals, minus 1.5 kilopascals. So we're going to have a technically dimensionless number here, but it never hurts to tell us that the humidity ratio is a comparison of masses. It's the mass of water vapor present in your air with respect to the amount of mass of dry air. So solving for this, we get 0.00928, and this is kilograms H2O in the air versus kilograms of dry air. Okay, so technically dimensionless, but actually represents something. It's a mass ratio, really. Part C is what's the dew point temperature in degrees C. The dew point temperature is the temperature at which dew would appear, okay, condensation would appear, if the air were to cool at constant pressure. So the dew point temperature is pretty simple. It's just a matter of determining the saturation temperature at the atmospheric pressure condition. So in this case, it's the saturation temperature at 102 kPa. So again, we just go to our table. We look up 102 kPa, and that's roughly 13 degrees C. Okay. The mass of dry air in kilograms. What's the mass of dry air in kilograms if the mass of water vapor is 10 kilograms? Well, this actually goes back to part B. Part B told us that the absolute humidity was 0.00928 kilograms H2O over kilograms of dry air. Therefore, if you remember that the absolute humidity is simply defined as the mass of your vapor in your air with respect to the amount of mass of dry air, this is actually how your absolute humidity is defined, then we recognize that we can just simply solve for the mass of dry air by rearranging this equation, mv over omega. The mass of vapor is provided for us. They say, what if it were 10 kilograms? What is the mass of dry air? So we divide this by 0.00928 kilograms H2O over kilogram dry air. In the numerator, this kilogram, 10 kilogram, that's of H2O. So kilogram H2O cancel out with one another. A per kilogram of dry air in the denominator means that the units are, as we should expect, kilograms of dry air. This is 1077 kilogram dry air. Last but not least, what's the volume of the room itself? And the volume of the room we can get from the ideal gas law. PV equals MRT. So in this case, we can just simply solve for V. This is going to be MRT over P. And if we only focus on the dry air component itself, then the pressure of the dry air, R of dry air, T of the dry air, the mass of the dry air, we could solve for it that way. We could also solve for the volume by considering MV, RV, TV over PV. Okay, these will get us the same values regardless of how we do this. So I didn't work this one out in advance, but if PV is equal to, or I'm sorry, if we were to consider this this last one here, as we want to solve it, the mass of the vapor that was given to us, that's 10 kilograms. RV, this is the specific gas constant, 8.315, I believe, kilonewton meters per kilomole Kelvin. I'm going to move this recording guide out of the way. Divide that by 28.97 kilogram per kilomole. That's going to be our RV. This whole term here is RV times the temperature in Kelvin. So that's 273 plus 30. So that's 303 Kelvin divided by our vapor pressure, which is provided for us 1.5 kilopascals. That's kilonewton per meter squared. So we'd have kilogram cancel out with kilogram, per kilomole, per kilomole, per Kelvin, and Kelvin cancel out. Kilonewtons and kilonewtons, meters squared in the denominator will come up here to multiply with the meters in the numerator, so that will leave us with meters cubed. And when we solve for this value, well, you know what? I'm just going to cheat here. I actually pulled up the solution just to check my work before I did this. There we go, 932 meters cubed. 932 meters cubed. Okay? Right. Can we get these same exact answers using the psychrometric chart? Oh, why is this thing so funky? Okay, here we go. Here's our psychrometric chart. It's developed for standard atmospheric conditions, which is pretty close to 102 kilopascals, generally 101.3, but that's totally fine. We're really close. So the question has asked us a number of things. It says that the large room contains moist air at 30 degrees C. So this 30 degrees C represents the dry bulb temperature, which is located along the bottom axis, the dry bulb temperature, 30 degrees C. So we're going to be along this line. Ooh, why not use colors? So we have somewhere along this line, we're going to intersect. Somewhere along this line we're sitting. Okay, 30 degrees C is the measure of the dry bulb temperature, just simply holding a thermometer up into the air. We had solved for the relative velocity, or not relative velocity, the relative humidity, and we found that it was about 35%. That corresponds to a point right here in blue. We have 30 and we have 40, and they sweep through these curves. So we're going to be halfway between 30 and 40, 35%. That's our state. That point represents the state in our room. Can we solve for these other parameters? Well, the first thing that we're asked to determine is the humidity ratio, or the absolute humidity. Absolute humidity is plotted along this vertical axis to the right. And all of these numbers are horizontal. These tick marks are horizontal. So in order for us to determine our humidity ratio, we would start with the point that we're located at, and we would move along this horizontal till we intersected with that line, and look where we are. We find that our absolute humidity, or humidity ratio, same thing, 0.009 units are kilogram H2O per kilogram dry air. This is exactly the same value that we found before. However, when we used equations, we have a more resolved answer. The benefit of the psychrometric chart is we just solved for our humidity ratio without having to use any equations. We just simply drew a line. What was the next thing we were asked for? Oh, what's the dew point temperature? The dew point temperature, it corresponds to a horizontal line drawn to the left from your state. Okay, so what's the temperature at this point? Well, right here, this is our 10 degree C line, and down to the right up here is our 20 degree C line. So we have 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we are roughly up here. We're at about 12.5 degrees C. We said that this was 13 degrees C according to our tables. Pretty darn close. Okay. So again, we're not quite as accurate as when we use the tables, but this is a lot faster. The dew point temperature is about 12.5 degrees C. At this point, the next question asks, what's the mass of the dry air if we have 10 kilograms of water? We'd have to use the same equation we did before, using the humidity ratio, or the absolute humidity. We'd solve for the mass of dry air present in our room. But that last part where it says, what's the volume of the room? We had to use the ideal gas law. That took some time. But if we look here, our point is located along a couple of these constant specific volume lines. So if I trace a couple of them, we can see how they act. So we have 0.9, we have 0.85, That means we would have 0.85, 0.86, 0.87, 0.88. So our dot is somewhere between 0.85 and, I'm sorry, 0.87 and 0.88. Our specific volume is about 0.872 meters cubed per kilogram. Now this is kilogram of dry air. So I'm going to put a little dA there to remind ourselves. So if we need to determine the volume of our room, it's just simply the mass of your dry air times the specific volume of your dry air. So the mass of our dry air we determined from before was 1077 kilograms times the specific volume, 0.872 meters cubed per kilogram dry air. When we solve for this, I use a slightly different value, I think, my calculation, but this will be pretty much nearly identical. Let me just pull up the calculator here. So if I perform this, 1077 times 0.872, it's going to be equal to 939. 939 meters cubed. We compare that to the volume that we had before, 932 meters cubed. Really close. So the advantage of using our psychrometric chart is that it's just a little bit faster, but you can get there either way. So there you go.